Hello, my name is Isabelle Costa. I'd like to talk about the study named Analysis of Different Wall Typologies, the Thermal Performance of a Naturally Ventilated Social Interest House. This study was performed with Professors Letícia Neves and Lucila Labac at the State University of Campinas in Brazil. The study is based on the importance of natural ventilation for thermal comfort, especially in hot humid regions. However, the use of natural ventilation is often impaired by the existence of nearby external elements, such as boundary walls or fences. Previous studies showed that the different walls configuration could change natural ventilation conditions in buildings, but less attention has been paid to effects of the geometry aspects walls on building thermal performance. These studies have emphasized the impact in the flow patterning and wind velocity, as you can see in Figure 1. So, the objective of this paper was to evaluate the influence of the different types of walls on thermal performance of residential buildings in Brazil. To aim this objective, we used parametric analysis performed by computer simulation. Firstly, we defined boundary walls models and variable parameters. We set 3 models of boundary walls, one without the opens, which is our reference model, and 2 with laminate components, being one with upward direction laminas and the other with downward direction laminas. The investigation considered a real single-family social interest residence. Also, we analyzed 2 variable parameters, 3 porosity of the wall and 3 wind incidence angle at the frontal facade. This definition generates 15 different cases. After, we simulate this case using EnergyPlay software. The study considered the weather data for the city of Maceió, located in Alagoas State in Brazil. The city has a hot, humid climate. We can see in Figure 3 the building geometry of study. This geometry contains 7 thermal zones. We use the flow network model for natural ventilation modeling, so for a flow calculation between thermal zones and the outside, we insert input data as the schedule for windows and doors opens, and the natural ventilation parameters, for example, the wind pressure coefficient. This parameter was inserted manually, based on data obtained in CFD simulation. Also, we consider only the permanently occupied rooms, which are bedrooms and living room. We compared the cases considering 3 variables: air change per hour, indoor air temperature, and degree hours based on adaptive comfort model. Besides, we simulate considering a typical day in summer for the city of Maceió, and we performed a yearly analysis too. I'd like to know to move on to the main results. In analysis of air change per hour, we observed that the model with downward direction laminate components and 75% porosity displayed the highest values, especially in bedroom with a wind incidence angles of 45 degrees. This can be seen when we look at the Figure 4, which shows the result of a typical day in summer. We noticed that during the time, this model obtained twice as many air changes per hour compared to the other models. However, the difference between models is small in the living room and bedroom too. The annual analysis shows similar results compared to the typical day analysis. Here you can see that the wall with downward direction laminate components displays a higher behavior than in other cases, especially in bedroom 1, with wind incidence angles of 45 degrees. Also, it's possible to see that the air change per hour variation following the wind velocity profile, being the highest observed values from October to March. We observed the same results in the living room, but in bedroom 2 there were little difference between cases. The indoor air temperature results were similar for all scenarios and the rooms. You can see in the figure that the indoor air temperature was higher than outdoor temperature, except for a short period in the morning. Bedroom showed lower values in the afternoon for the case with downward direction laminate components than other models. The results didn't show thermal discomfort due to cold, but a high number of cooling degree hours. This can be seen when we look at the figure 7, which displays the annual cooling degree hours for 3 analyzed rooms. In general, there weren't significant difference in values among cases, but you can see that the model with downward directional luminate components and 75% porosity showed the lowest values in most situations, especially in bedroom 1, which the difference between this case and the other models overtakes 20%. Thus, it's possible to conclude that the best results happen when the configuration had more porosity and the laminas direct downwards. These cases showed the highest exchange rates and the lowest for cooling degree hours. So this study showed an association between geometric parameters of boundary walls and the building's thermal performance conditions, but in general this association was zero. Although the porosity of the wall is an important variable, it may not be analyzed in isolation. Other aspects can influence, such as the wall component characteristic, for example the direction of the lamina, and the orientation of the rooms. In future research, we'll include other configuration of a boundary wall, especially the comparison with a building without the enclosing walls. Thank you for listening. If there are any questions, you can send us by email.